Okay, let's talk about static equilibrium. Static equilibrium is when all the forces acting on an object cause it to remain stationary. So there are multiple forces acting, but the object is not moving because all the forces are balanced out. There's no net force, there's no resultant force. The equilibrant is the force that, when added to an unbalanced system of forces, brings the system into equilibrium. So if you've got an object that's not moving, but there are forces acting, then we say it's in static equilibrium. If you've got an object that, with the forces acting, would be moving, would be accelerating, but you want it to stay stationary, then you have to add the equilibrant, the force that, when you add it, brings it into equilibrium. Let me give you a concrete example to make this clear. I'm hanging a picture on the wall. So the picture frame has weight, and we treat that weight as acting at the centre of the picture. That force is pulling it down. If that was the only force acting, the picture would fall down. We don't want the picture to fall off the wall. So what we do is we stick a nail or a pin or something into the wall, and we attach strings to the size of the picture, or sometimes attached in different ways. That's okay. So on the picture then, there's tension in this wire holding it up this way, and tension in this wire holding it up. And as a result of the tension in those wires, the picture doesn't fall. So the tension in these wires together make up the equilibrant. Now, if I were to give you numbers and get you to actually try and solve this problem, we don't always want to draw a nice, pretty picture frame. We draw what's called a free body diagram. The picture in the middle, we treat it as a point, a single point. There's weight acting down. T1 is acting this direction, T2 is acting that direction. And it doesn't matter if I don't draw the angles exactly right, because I'm going to draw in, if this angle is 20 degrees, that's the angle between T1 and the horizontal. And this one is 20 degrees over here as well. And then I can solve this problem with the free body diagram, and I don't have to draw a pretty picture frame or whatever the object is in question. So let me put some numbers in to show you how this goes. A wire with a breaking strain of 100 newtons is used to hang a 10 kilogram picture on the wall. What's the minimum angle needed between the frame and the wire to support the picture? So it's the same situation as we had before. So I'm going to use the same kind of free body diagram to work it out. My picture is here, and it's 10 kilograms. The weight force, we'll work out in a moment, is its mass times g. The tension in the wires goes like this, and the breaking strain is 100 newtons. So if I were looking for the limit, we make both of those tensions be 100 newtons. And I need to work out the angle between the frame and the wire. It's going to be this angle. Unless we get told otherwise, assume it's the horizontal angle I'm looking for. Now these are the same force, so the angle will be symmetric. It's the same on both sides. Okay, I need to work out the forces. This is mg, which is 10 times 9.8. So that's 98 newtons. I need to balance my forces. Horizontally, there's no problem. The two tensions are balanced, and the weight force doesn't contribute to a horizontal force. So let's work vertically. What I have to have for equilibrium is the upwards net force being the same as the downwards net force. Well, the upwards net forces come from these T's. They're 100 newtons, and I'm interested in this part, this component of that vector. Well, that's going to be 100 sine theta. So 100 sine theta from T1 plus 100 sine theta from T2, both of those upwards components, T1 and T2, have to equal the weight force downwards, 98 newtons. Well, that's 200 sine theta equals 98, which means sine theta is 98 over 200, which means theta is arc sine of 98 on 200. I'm going to need my calculator. Inverse sine of 98 on 200, which is 29.3. I'm just going to make sure I'm still in degrees. That's good. 29.3 degrees. And there's the solution. Here's another example. My job is to find the equilibrant. That is, to find the force that I would need to apply in order to balance out these forces and get into static equilibrium. So, to do that, the simplest way is to add these forces together, remembering their vectors, do a vector addition, work out the resultant net force, which will be this sort of direction somewhere, I'm guessing. Then the equilibrant is the same magnitude in the opposite direction. That's going to be the equilibrant. So let's work out the resultant of these three forces. And again, if you're comfortable in Math C doing I's and J's, feel free. I'm going to do a slightly simpler thing, just looking at horizontal and vertical and keeping it that way. So horizontally, to the right being positive, I've got the first force, the second force, the third force. I'm going to do it in that order so that I don't get confused. The first one's 120 at this. I'm looking for the horizontal component of that, which is 120 cos 30. Cos 30. Plus, this one contributes 100 in that direction. The third force doesn't contribute at all to the horizontal direction. So that, here's my calculator, is going to be, where can I put it so you can see it? Check I'm in degrees. I am, so 120 cos 30 plus 100, 203.9. Given the low number of significant figures in my question, I could probably just call that 204. I prefer to go maybe one extra digit for now, and I'll fix that later. Okay, so that's 203.9 newtons across. What about vertical? Let's stick to our convention that up is positive. Upwards, this first force contributes 120 sine 30. 120 sine 30. Plus, second force doesn't contribute to the vertical at all. Third force contributes 140 newtons negative. Negative 140. So, 120 sine 30 minus 140. I've got negative 80. Negative 80 newtons. So, my resultant force looks like this. 204 that way, 203.9, and 80 downwards. I'm looking for this first of all. That's my resultant force. Well, the size of my resultant is the square root of 203.9 squared plus, it's a 9 and a decimal point, plus 80 squared, which is the square root of 203.9 squared plus 80 squared, 219. That's great. 219 newtons. And I need the angle. Let's go for this angle here. That angle is the arctangent, the inverse tangent of 80 over 204. 80 over 203.9, which is shift tan of 80 over 203.9, 21.4 degrees. 21.4 degrees. Okay, if that's my resultant force, it's going this way, then my equilibrant is this direction. That's my equilibrant. Okay? So, my equilibrant then is the same magnitude but the opposite direction. So if this is 21.4, that was my resultant. If this is 21.4 degrees, I want 180 degrees away from that. So if I go 180 minus the 21.4, I'll get this angle, which is the angle I want. Okay? So my equilibrant is, that was meant to be an E, 219 newtons at 180 minus 20, which is 160, so 158.6 degrees. Or draw it on the diagram is just as good because it shows that you know which way it's going. Now, the last example in the slides, in the PowerPoint slides, is much more complicated. So I'm going to leave that for another video.